All right. Yeah, thanks for joining. Today we are very happy to have Peter, who is a friend of mine and a friend to many people in the TIBA community. Peter is the former president of TIBA. He recently graduated from Tsinghua with a master's degree in advanced computing, and he's now working full-time at Conflux as a principal software engineer. So without further ado, Peter, thank you so much for doing this, and the stage is yours.
Yeah, thank you. Hopefully you can hear me now. So with that, I will get started. So yeah, hey everyone. I appreciate that you joined us tonight or today, depending on your time zone. I know everyone is very busy with the midterms. Yeah, today we'll talk about the consensus mechanism of Conflux. So basically what I'll try to do is to, I will repeat some of the stuff that you've learned before about how consensus works in Bitcoin. I will emphasize some parts that are relevant to our discussion. And then we'll move on to discussing how Conflux is different. What Conflux introduced, some new mechanisms to make Bitcoin more scalable while maintaining its decentralized and secure aspect. So yeah, let's get started. Yeah, first of all, a bit about me. So my name is Peter, and I actually just graduated from Tsinghua this year. I was doing a master's in computer science from 2018. And yeah, I graduated, but before I graduated, I had the honor to serve as the previous president of TIBA. So I'm very happy to see that Sam and the rest of the members of TIBA are doing such a great job, giving you all these great events and stuff. And thanks for the invitation, by the way. So before I graduated, in my second year of my master's, I joined Conflux as a research engineer, and now I'm working there as a full-time engineer. So first of all, let's talk a bit about the motivation. Like, why do we care about scalable blockchains? So this triangle, some of you might have seen it. This was coined by Vitalik from Ethereum. So he calls it the scalability trilemma of blockchain. And the idea is that there are three main components that we want to achieve in blockchain, or three main aspects. One is scalability, the other one is security, the third one is decentralization. So maybe I will talk about security first. So security is probably the most important aspect. It would say that your system is secure, right? So for instance, on Bitcoin, you should not be able to do a double spend attack. So that's kind of the main security component. Scalability is generally the performance of a blockchain. So let's say transaction throughput. And that is the main bottleneck, let's say, or the main shortcoming of public blockchains now. So on Bitcoin and Ethereum, you have like 10 transactions per second. So it's by far not enough for most applications. And decentralization is the main selling point of blockchain, I would say, because many of the services that blockchain offers can also be provided by governments or banks or private companies. But many of us in the blockchain community really believe in the value of decentralization. So the value that we don't rely on one single centralized authority, but instead there's a decentralized global network of computers. It kind of makes it more democratic in a way. So as I said, Bitcoin has a scalability problem. Same is true for Ethereum, although they are trying to solve it with Ethereum 2.0. And Bitcoin also has a decentralization in their own computers, but then they started this kind of arms race of hardware. So people moved on to GPUs and then moved on to ASICs, which are custom-made hardware, so made specifically for Bitcoin mining. And the problem with ASICs is that it increases the entry barrier for normal users. So before you could just mine with your own computer, with your laptop, maybe even your laptop, but now you need to purchase specific hardware to be able to make it profitable. You need to use a lot of electricity. So in the end, most normal users cannot really mine. So there's this kind of centralized aspect of Bitcoin mining. Anyway, what the scalability trilemma claims is that these three goals of blockchain it's probably not impossible to attain all of them at once, but it's very hard because there's always certain trade-offs between them. But 2 years ago, when Conflux was founded, our founder, Longfan, he believed that, okay, there are trade-offs to be made, but we're by far not at the level of the hardware yet. So basically, the hardware is not the bottleneck of blockchain scalability. And we can look at some of the numbers for this. So if you look at peer-to-peer networks today, that means like what is the speed of block propagation or transaction propagation. Basically, you could easily achieve thousands of transactions per second with a average internet speed. If you look at storage, that could be the other bottleneck. Disk reads, disk writes. With an SSD, you can actually achieve much higher transaction throughput. So this is not the bottleneck either. And we talk about computation, so that would be CPU or even GPU. One of the most costly parts is transaction signature verification. But even with that, you could achieve thousands of transactions per second. So the hardware doesn't really account for the bottleneck that we experience in Bitcoin and Ethereum today. And if we visualize it like this, what is the bottleneck of the system? We see that network is probably not the bottleneck. Computation is not the bottleneck. Storage might not be the bottleneck. What we experience is actually that consensus is the bottleneck in Bitcoin. So what I mean by this, and what you will see shortly, is that if we try to use Bitcoin's consensus to achieve higher TPS, as we increase the throughput, the security of the system will suffer. So there is really a trade-off to be made, but that is mostly due to, it can be alleviated by having a more high-performance consensus mechanism. So that is the basic idea or the motivation between these new techniques. So to understand these trade-offs in Bitcoin, we need to talk about the main components of the Bitcoin consensus. And first of all, what is consensus? So in terms of blockchain or public blockchains, I would claim that we need to reach an agreement on which transactions happened and in which order. So let's say I send you a transaction, let's say I buy a coffee from you, and then you spend that money to buy something else. So there's transaction A from me to you, and then transaction B from you to someone else. It can be this way, but it also can be the other way. So transaction B first and then transaction A. Of course, in this way, if you don't have money first, then your transaction will fail. The point is that from the network's perspective, there's no inherent order between transaction A and B. What we want to achieve is that everyone should agree on either A comes first, B second, or the opposite. So we need to reach consensus on this. And you're probably familiar with how Bitcoin achieves this. I would say there are 3 components. People usually say it's proof of work consensus, but I would say it's actually 3 components. So one is the blockchain, which is actually a block tree, as you will see. There is a thing called the longest chain rule. And then finally, there's a technique called proof of work. So let's look at these in more detail now. So in Bitcoin, the ledger structure is what they call blockchain or block tree. First of all, we have blocks. And what I mean by that is that miners or the creators of this block will collect a certain number of transactions, let's say 20 transactions, 200 transactions, and they group them together into sort of blocks. So essentially, a block is just a collection or a list of transactions. And we also have some metadata called the block header, but that's more like an implementation thing. Okay, so a block is just a collection of transactions. And what makes it into a blockchain? Well, each block will reference exactly one previous block, and that is called a parent block. So what I mean by that is, let's say we have this block here. Hopefully you can see my cursor so that I'm pointing on the second block here. And the second block, apart from the transactions, it will also contain the hash of the first block. The third block will contain the hash of the second block, etc., etc. So you know that the hash is basically a unique identifier of all the blocks data. So in this way, blocks are chained together, and that is why Bitcoin introduced this thing called the blockchain. It's just a chain of blocks. So why is it good to have a chain of blocks? It basically achieves our goal or solves our problem. Basically, a chain of blocks will define the canonical transaction order. So you can see, let's say, transaction 2 and 3. They have a specific order in the block, So we can see that transaction 2 will come before transaction 3. Similarly, between blocks, you see a clear order. So transaction 1 will come before transaction 2. Transaction 1 will also come before transaction 4. So as long as we have the transactions in such blocks that are chained together, it's very easy to reach consensus on the total order of transactions. Now the problem is that each block has exactly one reference, but what happens if we have concurrent blocks? So blocks created roughly at the same time. So here we see 2 blocks that are referencing the same parent block. So both of these blocks will have the same parent block hash. Now you can see that this becomes an issue because our nice chain of blocks is actually not a chain now, but a graph. So we call it tree in graph theory. And yeah, it makes it harder to choose the transaction order, right? It messes with the system. Yeah, so for instance, on the top fork, we might have transaction A in this block and transaction B in this block. And maybe on the other fork, we have it in the different order. So transaction B first, transaction A first. So which is the real order? Now we need another rule to be able to choose between these 2 orders. And that is the longest chain rule. So you can see that with the very simple ledger structure of Bitcoin, we might have concurrent blocks. These are also called forks, as I mentioned just now. The question is, how do we choose between these 2 forks? And the technique that Bitcoin uses is a very simple rule, which is called the longest chain rule. So if you see 2 chains, you will always choose the longer chain. So in this example, we will have this chain on the bottom, and these 2 blocks on the top will be discarded. So we will choose the longest chain. From the miner's perspective, so the miner is the person that's creating the blocks. Let's say the miner sees this ledger. So the miner will choose to create the block on top of the longer chain, not the shorter chain, as long as the miner follows the protocol. So eventually, the majority of the network should converge to this chain, and the other chain will be discarded. So the longest chain rule in Bitcoin is used to break these ties between forks, so to say. And finally, proof of work is also a very crucial component of the system. So if you just look at, let's say, a chain here, you see the longer chain, but what stops you from creating a longer chain if you're an attacker? So just creating a block should be, normally it would be very easy. You just collect transactions, you can create blocks, send it to the network. So basically you could do it like thousands of blocks per second, even with such speed. So what stops you from creating a longer fork that changes the transaction order? Well, what will stop you is proof of work, which is basically a way to artificially make it harder to create blocks. So instead of allowing you to create many, many blocks each second, at least in Bitcoin, it's set in a way that the whole network can only create 1 block every 10 minutes on average. So all the computers are calculating. At one point, someone finds this magic number called proof of work, which makes the block valid. And then the rest of the network will accept the block. Now, if an attacker wants to create a competing fork, as long as he has less than half the hash power of the rest of the network, he can't keep up with the network. So imagine that the majority of the miners create blocks on the bottom fork. So they will always create more blocks than an attacker that wants to create a fork. So without going into too many more details, I think you're mostly familiar with the ideas here. So that is the main use of proof of work in my understanding. All right, so now you see how these 3 components coming together in Bitcoin to achieve consensus on a linear order of transactions. Now the problem is with these discarded blocks. So as I told you, with the longest chain rule, you choose the chain and you discard the rest of the blocks. The problem with this is that the discarded blocks do not contribute either to the security or the throughput of the system. So can we do better? Well, let's see what I mean by this not contributing to the system. So let's say we want to increase the performance of Bitcoin, and a straightforward way would be to increase the block creation rate. So instead of 1 block every 10 minutes, you could have 1 block every 10 seconds. So that could definitely increase the TPS, right? Now the problem with this is that blocks need time to propagate to the peers. So if you create a block, maybe it takes 10, 20, or 60 seconds for it to reach the rest of the network. So that means that if you have higher block creation rate, that would result in a higher fork rate. So more forks in the ledger. Now more forks could be okay because you can still use the longest chain rule, right? So you choose this chain and then you discard all the other forks. Now the issue with this is that the more forks you have, the less honest computing power is maintained on the longest chain. So you see that there are 8 blocks here, but only 3 of them is kept. So basically only 3/8 of the computational power is invested into the longest chain. And simply put, that means that it's much easier to attack this system than a system where there's only one chain instead of many chains. So you see that on Bitcoin, increasing the block creation rate actually decreases the security of the system. The other issue is that, okay, we have 5 blocks here that we discarded, and all those 5 blocks can have many, many transactions, real transactions that real users try to send. So all of those transactions need to be discarded. So they don't contribute, they're not processed, they don't contribute to the throughput of the system. So even if you increase the block creation rate, the throughput might still not scale directly with the number of blocks. So that is the other issue. Now, to address the first issue, we will use another chain selection rule called GHAST instead of the longest chain rule. So let's look at this ledger example. You see that here we have many concurrent blocks, many forks. And if you execute the longest chain rule, it will choose this chain here, right? Because this has 4 blocks, while in the other branch, the longest chain is 3 blocks. Now the issue here, as I mentioned on the previous slide, is that basically 4/9, so less than 50% of the computational power works on this chain. So this is actually a minority. The majority of the computational power works on this fork. Now GHAST, on the other hand, will select this chain by always looking at the overall number of blocks in a subtree. So let's look at these numbers. So here you can see that the subtree starting from here, so these 5 blocks, it has 5 blocks. So let's say it has a weight of 5. Let's say each block has a weight of 1. As opposed to this, the other chain, the longest chain, will only have 4 blocks. So the weight of this subtree will be 4. So what GHAST does is it goes from block to block, and at each block with multiple children, it will choose the one with the highest weight. So here we look at these 2. This has 4, this has 5, so we will select 5. This one has 3 child blocks with weights 1 to 1, so it will select the one with the weight 2, and etc., etc. So this is actually much harder to implement, but this is a much more robust chain selection rule because it will always choose the chain with the majority, hash power. So that's the basic idea of GHAST, which, by the way, stands for greedy heaviest observed subtree. So this is a subtree, this is another subtree, and this subtree on the top is heavier. So again, with GHAST, we will always choose the subtree with the majority of the hash power, and this makes GHAST more resilient, even if we have a high block creation rate, even if we have many, many forks. And by the way, the GHAST protocol was published in 2015 by these Israeli researchers. Now we see that GHAST is more resilient under high block creation rates, but can it still be attacked? And the answer is yes, there is a different kind of attack on GHAST. And this is called a liveness attack. So the idea here is that normally, let's say a blockchain could confirm a transaction in 30 seconds. So that means that after 30 seconds, you can be sure that your transaction is not reverted. Now, what happens if the attacker can extend this time so that you wait 1 minute, 5 minutes, 10 minutes, maybe hours, and even after hours, your transaction is not confirmed? Now, that is an issue because that severely impacts the usability of the blockchain, right? If you cannot confirm your transactions, then you cannot use it, or you cannot spend that money that is not confirmed that it belongs to you. And this attack exists on GHAST. So let's look at this scenario. Let's say we have 2 forks, and normally the majority of the network would converge one or the other. So after a while, the whole network, let's say, would converge to the top fork. But if an attacker pre-mined a lot of blocks, which don't need to point to the tip of the ledger, but they can point to, let's say, these 2 blocks. So you can, with a minority hash power, you can pre-mine many blocks, and you can release them to the network selectively. So let's say the network mines this block as the next block, and this actually, it breaks the balance, because now here we have 4 blocks, now here we have 3 blocks, so this is heavier. At this point, the miner can release this block, so the attacker block, to restore the balance. So now we have 4 blocks, now we have 4 blocks. Let's say the network then mines the block here, so this also breaks the balance. Now it's 5 blocks versus 4 blocks. Then the attacker releases another block. So there is the basic idea that the attacker cannot do a double spend attack, but they can, make the system unusable by performing this liveness attack or balance attack. So that is an issue with GHAST. To address this, Conflux uses a modified version of GHAST called GHAST, so greedy heaviest adaptive subtree. And the idea is that just looking at the ledger, the miner actually detects if an attack is going on. So let's say you see this ledger, you see the 2 long forks, and you see, oh, maybe there's an attack going on. So with high probability, there might be a balance attack going on. And at this point, the miners deterministically switch to another mode, which is called the adaptive mode, which changes the rules of the consensus a bit. And it changes the rules so that each block has a weight of 0, and some very rare blocks will have very high weights. So the network will keep mining, and at some point, the whole network will find one special block with a very high weight that will really break the balance and will cause all the miners to converge to this fork. And this is extremely hard for an attacker to counter, because even the attacker doesn't have enough hash power to create such a high weight block. So again, we switch to adaptive mode, and in adaptive mode, certain special blocks will break the balance, and it will make the liveness attack fail. So that is basically the difference between GHAST and GHOST. So again, this stands for greedy heaviest adaptive subtree. And this is the chain selection rule that is used in Conflux. Okay, so we discussed GHOST, and we discussed how GHOST helps it lets the main chain be more stable, even if we have many forks. And we also talked about GHAST, which makes the chain more resilient against liveness attack, which would make the system get stuck. But we talked about the other problem too, right? That discarded blocks in Bitcoin and other systems do not contribute to the throughput of the system. So is there a way that we could increase the throughput? Is there a way that we could still use those blocks to process transactions? Now, the solution that we use is called tree graph, which is a different ledger structure. So if you look at this simple fork in the blockchain, and let's say we create a new block called C. So if you look at the blocks A and C, there is an order between them, right? So you can see that A existed when C was created. So A came before C. The problem is that there is no order between B and C. So maybe B was created first, maybe C was created first. We cannot know because we were not there when they were created. We only have this information. And this makes it very hard to incorporate the transactions in B into the ledger. What we will do instead is that we will introduce additional information. So before we only had the parent edge, which points from C to A. Now we introduce a new kind of edge called the reference edge. And C will have a reference edge to B. So the idea here is that each block will have exactly one parent edge. So that's the same as with Bitcoin or Ethereum. But a block can have 0, 1, or more reference edges, and the block must reference all unreferenced blocks at its creation. So C will reference B. And this actually gives us a lot of extra information because we know that, okay, B existed before C. So in order for C to reference B, B must have existed because you need to know the hash. And this will allow us to actually derive a total order of all the blocks. The additional information will help us derive an order. If you look at a more complex example, so here we have this example. And so why is it called tree graph? Well, if you only look at the parent edges, so that would be the, parent edges, so that would be the solid arrows. then you see a tree. So a graph that is a tree, right? There's no cycles in it. Yeah, but if you look at all the edges, so parent edges and reference edges, then you see a more complex graph called a DAG, or directed acyclic graph. So there are basically two different perspectives on this graph, which is essentially a DAG. But because these two different perspectives, we will call it the tree graph. So to process this ledger, first you will execute GHAST on the parent tree. So you only look at the parent edges, and you can look at the subtree weights, right? So for instance, with this block on the top, the subtree weight is 1 because it doesn't have any parent edges pointing to it. If you look at this block here, it's 2 because there's 1 block and then 2 blocks. And yeah, based on this approach, you can set all the weights, and then you can selectively choose the subtrees with the highest weight, and it will end up selecting this main chain. This is actually called the pivot chain in Conflux. So once you've selected the pivot chain, which is basically the backbone of the ledger in a way, then you will divide the ledger into epochs in a deterministic way. So what I did here is I kept the same edges. So it's basically an isomorphic graph. It's the same graph. I just moved the graph around a little bit. And this will be one epoch. So an epoch can be one or more blocks. The way it's defined is that each pivot block, so each block on the main chain, will define one epoch. So this is epoch 1, 2, 3, etc. And then for the rest of the blocks, we will assign them to epochs with a simple rule that the block belongs to the epoch, the first epoch from which it's reachable. So let's look at this block on the top. It is not reachable from epoch 1, so there's no edge going from this block to this block. It is not reachable from epoch 2 either, but it is reachable from epoch 3. So if you go through this edge and this edge, you can reach this block. So you see that epoch 3 has both of these blocks. Similarly, these 3 blocks will belong to epoch 4. And yeah, you can get the basic idea. This is basically a deterministic way to divide the tree graph into epochs. And by deterministic, I mean that all the nodes in the network will agree on this. So everyone who executes this algorithm will reach the same result. Now, the cool thing about epochs is that now we can use this to actually order the blocks. And there's a very simple rule for that too. First of all, blocks in an epoch will come before the blocks in the next epoch in the order. And within one epoch, you will see you will use a simple topological sorting. So in this example, we could reach this final order of blocks. So we have 1, 2. Within this epoch, we have the 3rd block, 4th block, 5th block, and 6, 7, 8. So you see that even though some of the blocks are unrelated, we can reach consensus on the total order of the blocks in the tree graph. And finally, so originally we didn't care about the order of the blocks. We only care about the order of the transactions. The good thing about a block ordering is that it will basically give us a transaction ordering, right? So if we have a bunch of transactions in the tree graph, then we can divide it into epochs, just like we did before. And the order of the blocks will define the order of the transactions. So this block will come before this block. So we will have transaction A first, then B, C, D, E, C, F, G, F, E, H. So we follow the block order, and that will give us a transaction order. One interesting difference between, let's say, Bitcoin and Conflux is that Conflux can have the same transaction multiple times. So in concurrent blocks, you could have the same transaction. For instance, we have transaction C here and here again. So in the total order, we also have 2 instances of transaction C. The way we will handle this is that, generally speaking, we will only accept or execute the first instance of a transaction. So this transaction C is executed, and the second one is discarded or ignored. And now you can see that with the tree graph, we actually managed to include all the transactions in the ledger and not just the transactions in the main chain. So to summarize, today first we discussed how Bitcoin uses proof of work and the longest chain rule to achieve consensus on a linear sequence of transactions. So we had a chain of blocks, and this chain of blocks defined a sequence of transactions that we could execute. We talked about GHAST, the greedy heaviest adaptive subtree chain selection rule, and we saw how it allows the main chain to remain stable with many forks, and it is also resilient against liveness attacks. So that is the chain selection rule used by Conflux. And we also talked about a new ledger structure called the tree graph, which allows us to keep transactions from all blocks. So not just the main chain blocks, but also from concurrent blocks of the main chain. So that is basically the two main ideas behind Conflux: GHAST, chain selection rule, and the tree graph ledger structure. Yeah, so that was basically a simple introduction, hopefully not too complex introduction to the main ideas behind Conflux. And if you want to learn more, you can reach out to me, or you can also look at some of these resources that I included. So these are the presentations and papers relevant to this discussion. And yeah, thanks for having me, and thanks a lot for listening to me.
Thank you, Peter. If you have any questions, so we'll have some time for Q&A. If you have any questions, put them in the chat, or just open up your mic. And but I guess I can get started with one question. You know, many projects look into changing, instead of the longest chain part, they look into the proof of work part and change that to proof of stake or other kind of ways to reach consensus. Has Conflux looked into the possibility of that?
Yeah, so using, let's say, proof of stake instead of proof of work.
Yeah.
I think at some point it's a philosophical issue, like whether you believe in proof of stake or not. The problem for us with proof of stake is that it hasn't proven itself yet. So
Right.
Ethereum is hardly, it's really looking into proof of stake, and yeah, hopefully it will work out for them. But there's no large scale system that's really using proof of stake, as opposed to proof of work that has proven its resilience for like 10 years or more with Bitcoin. So I think that's one of the reasons that we use proof of work. And proof of stake has a series of open questions that I'm not sure they're all addressed. So how do you bootstrap the system if no one has coins? These kinds of problems. But we will see. I hope that it all works out for Ethereum and the other people working on proof of stake. But Conflux chose proof of work as its approach.
All right.
If you have any questions later, then you can just ask me in the group. So no worries about that.
Yeah. I guess we'll finish with this question. Where do you think Conflux is going in the future from now? Because the main net just launched. Where do you think it's going from this point?
Yeah, this is a very exciting time for us. So the mainnet just launched like 3 weeks ago.
Yeah.
I think Conflux is a very unique place, being based in China, but of course we are aiming to be a global public blockchain. So what we will see for the next 1 or 2 years is a gradual growth. So we want to see more projects built on Conflux, and we want people to use its unique features, which is high TPS and transaction sponsorship. Each blockchain project has the same dream, which is wide or mainstream adoption of blockchain.
Right.
I think that's what we're aiming at by solving some of the fundamental issues that other projects have. So let's see how it works out. I'm very optimistic.
Nice. All right. Yeah. So I guess that will be it for this workshop. Again, thank you, Peter, for the amazing lecture.
Yeah, thank you for having me.